One galaxy in the early universe has already stopped growing. It stopped spinning. It stopped making stars altogether, less than 2 billion years after the Big Bang. Nothing in our models says that should be possible this early, and yet there it is. It's not alone. Across the deepest images ever taken of the sky, dozens of galaxies look decades too old for their age, too bright, too heavy, too still. Some answers have already emerged. Others are stranger than the mystery they were meant to solve. One thing before we begin: if you're the kind of person who's always been drawn to deep space, subscribe. It helps us reach more minds like yours. We're genuinely glad you're here. Now, let's begin. Let's start with a number. The universe is about 13 billion years old. That's not a rounded guess. It's a figure pinned down by multiple independent methods, from the leftover glow of the Big Bang to the way galaxies drift apart from each other. Keep that number in your head. Almost everything in this video is measured against it. Here's the part that trips people up. When we look far away in space, we're not seeing things as they are. We're seeing them as they were. Light takes time to travel, and the universe is big enough that time to travel can mean billions of years. A galaxy sitting 12 billion light-years away isn't showing us what it looks like today. It's showing us what it looked like 12 billion years ago, back when the universe itself was young, dense, and still figuring out how to make galaxies at all. This is what astronomers mean when they talk about looking back in time. It's not a metaphor. It's a direct consequence of the fact that light isn't instantaneous. The farther out we look, the further back we see. Push that far enough, and you're not just looking at old galaxies. You're looking at the process of galaxy formation itself, caught in the act, a few 100 million years after everything began. Try shrinking that timeline down to something you can actually hold in your head. If the entire 13 billion-year history of the universe were compressed into a single 24-hour day, the earliest galaxies this video is about would appear in the first few minutes after midnight, while the sun, the Earth, and everything on it wouldn't show up until well into the evening, somewhere around 9 p.m. Everything we're describing in this video happens in that first sliver of the night, long before anything resembling our own solar system existed at all. There's a second wrinkle worth understanding now, because it comes up again later. The reason distant light shifts toward infrared isn't just that it's traveled a long way. It's that the space it's traveling through has been stretching the entire time, expanding in every direction, and stretching the light's wavelength along with it, a phenomenon called cosmological redshift. The more the universe has expanded since a photon left its source, the more that photon's wavelength gets stretched toward the red end of the spectrum and eventually past visible red into infrared entirely. So looking for the very earliest galaxies isn't just about looking far away. It's specifically about looking in infrared, because by the time that light reaches us, infrared is the only kind of light left to find. For most of the history of astronomy, that window was essentially closed. The light from those first galaxies is so faint and has been stretched so much by the expansion of space that it falls almost entirely into infrared wavelengths, invisible to the human eye and invisible to most telescopes. The Hubble Space Telescope, for all it accomplished, could only just barely glimpse the edge of that era. Then, on December 25, 2021, a telescope built specifically to solve that problem left Earth on top of an Ariane 5 rocket. The James Webb Space Telescope carries a primary mirror 6 meters across, more than twice the diameter of Hubble's, built from 18 hexagonal gold-coated segments that unfolded piece by piece once Webb reached space. Its instruments are tuned for infrared light specifically, the exact wavelengths where the earliest galaxies in the universe would be hiding if they were there to find. Webb didn't orbit Earth the way Hubble does. it settled nearly 1 million kilometers away, at a gravitationally stable point called L2, trailing the planet on the night side, shielded from the sun by a sunshield the size of a tennis court, folded down to almost nothing for launch and unfolded, layer by layer, over the following weeks. That distance and that shielding matter for a simple reason. Infrared light is, essentially, heat. A telescope built to detect the faintest infrared glow from the edge of the universe has to be colder than almost anything else humans have ever put into space. Otherwise, its own instruments would drown out the signal it's trying to see. Getting that cold that far away is most of why Webb needed 6 months of preparation before it could open its eyes. On July 12, 2022, after that preparation was complete, NASA released Webb's first full set of science images. One of them, a single patch of sky, no bigger than a grain of sand held at arm's length, showed thousands of galaxies packed into the frame. Astronomers had a name ready for what they expected to find in images like this: small, faint, ragged-looking galaxies still assembling themselves out of gas and the debris of the first generation of stars. That's what every model predicted. That's what decades of theory said had to be true. That is not entirely what they found. Within weeks of the first images being released, astronomers scanning Webb's data started flagging objects that didn't belong. Galaxies that looked, by every available measurement, far too developed for how early they appeared to be. Too bright, too massive, too structured. As if something had fast-forwarded parts of the universe's childhood. That's the tension this video sits inside. Not one single discovery, but a pattern, one that Webb has kept turning up again and again since the moment it opened its eyes. Some of that pattern has since been explained. Some of it hasn't, and the most extreme example, the one that anchors the back half of this video, is stranger than anything astronomers were braced for. Let's start at the beginning, with the shock that started it all. The reaction in the weeks after July 2022 was not subtle. Researchers were sending each other candidate images and running the same phrase past their colleagues, half joking and half serious. This might break cosmology. Here's why that phrase got used. The standard model of how the universe evolved, often shortened to lambda CDM, built on dark matter, dark energy, and a well-tested rulebook for how gravity pulls gas into stars and stars into galaxies, makes fairly specific predictions about how fast galaxies should grow. Gravity needs time to pull matter together. Stars need time to form, live, and die, seeding the next generation. Galaxies need mergers, accumulated over hundreds of millions of years, to reach any serious size. Run those predictions forward from the Big Bang, and there's a hard ceiling on how big and how bright a galaxy is allowed to be at a given age. It's not a guess. It's arithmetic, built on physics that has passed every test thrown at it for decades. Webb's earliest candidates didn't just brush up against that ceiling. Some of them appeared to blow straight through it, showing up looking as massive as galaxies that, by the clock, shouldn't have existed for another billion years or more. To understand why that's alarming, it helps to have a comparison you can actually picture. Imagine tracking a country's population growth using nothing but birth records, migration data, and average family sizes, a model that's worked reliably for 100 years. Then someone hands you a photograph of a city from year one of that country's founding, and the city already has the population your model says it should reach in year 80. You don't throw out arithmetic. You start asking what you got wrong about the picture, or what you got wrong about the model. That was the position astronomers found themselves in. Some early headlines leaned hard into the second option, that the standard model of cosmology itself might be in trouble. It's easy to see why that framing spread. It's dramatic, and there was, briefly, real uncertainty about whether it might be true, but science does not resolve itself through headlines. It resolves through follow-up observation, and the follow-up observations on these first candidates took time to gather deeper images, time to collect spectra instead of just brightness estimates, time to rule out simpler explanations. Here's why that distinction, brightness estimates versus spectra, actually matters, because it's the difference between a guess and a measurement. Webb's first pass at these distant galaxies mostly relied on something called photometric redshift, essentially estimating how far away and how old an object is based on which colored filters it shows up in and how bright it looks through each one. It's a fast, useful technique, and it's how astronomers flag candidates worth a closer look, but it's an estimate, not a confirmation, and estimates can be wrong. One widely publicized candidate, cataloged as CERS 93316, was initially estimated at a redshift, suggesting we were seeing it just 250 million years after the Big Bang, a jaw-dropping number. When astronomers went back with Webb's spectrograph and took an actual spectrum, splitting the object's light into its precise wavelength fingerprint rather than just its color through a few filters, the true answer turned out to be far less extreme. The object was real, but much closer, much later, much less exotic than the first estimate suggested. That's the process working as intended. Surveys like JADES, the JWST Advanced Deep Extragalactic Survey, spent the following 2 years methodically doing exactly this, taking spectra, one galaxy at a time, of the most promising early candidates, confirming which ones held up and which ones didn't. Some of the most extreme early candidates didn't survive that process. A few turned out to be nearer, more ordinary galaxies whose light had been misread. Others held up under direct spectroscopic confirmation and got stranger the more closely they were examined, genuinely ancient, genuinely massive, genuinely difficult to explain. One of those survivors is worth naming directly because it's the clearest illustration of the whole problem in a single object. In 2024, the JADES team confirmed a galaxy called JADES GSZ140 at a redshift of 14, light that left its source roughly 290 million years after the Big Bang, only about 2% of the universe's current age. That confirmation held up under a full spectrum, not just a color estimate, and what that spectrum revealed was not a faint, struggling smudge of a first galaxy. JADES GSZ140 turned out to span more than 1/600 light-years. Carrying an estimated 500 million times the mass of our Sun, in stars 5 times more luminous than the previous distance record holder, and showing signs of a strong burst of star formation in just the few million years before it was observed. Team member Stefano Carniani summed up the reaction plainly. It was stunning that the universe could build a galaxy like that in only 300 million years. This wasn't a misread color estimate. It was a fully confirmed, thoroughly measured galaxy, and it was still bright and massive enough to make astronomers uncomfortable. One useful piece of context: even before Webb launched, nobody expected the early universe to look exactly like a smaller version of the universe today. The first stars were likely more massive and burned hotter than typical stars now, because the raw material they formed from, almost pure hydrogen and helium, without the heavier elements later generations of stars would produce, behaves differently under gravity. Star formation in that environment might simply run faster and hotter than our intuition, tuned by a universe 14 billion years further along, would suggest. That distinction matters because it separates two very different kinds of surprise. One kind of surprise says, our fundamental model of the universe is wrong. The other kind says, our model of the universe is fine, but our assumptions about how quickly stars and galaxies could get organized in an unfamiliar chemical environment were too conservative. Both are interesting. Only one of them rewrites physics. Consider what the earliest possible generation of stars, sometimes called population III stars, would have actually been made of. Every star that has ever formed since is built from a mix of hydrogen, helium, and progressively more of the heavier elements forged and scattered by earlier generations of stars. The very first stars had none of that. They condensed out of almost pure hydrogen and helium left over directly from the Big Bang, with essentially nothing to help gas cool down and collapse efficiently. Under those conditions, current models suggest these first stars formed unusually large, burned unusually hot, and lived unusually short lives compared to stars forming today. A galaxy built rapidly from many such stars in quick succession might reasonably look brighter and more evolved earlier than a naive model, one built from local, present-day assumptions about star formation, would predict. That's not evidence of broken physics. It's a reminder that our intuition about normal, star formation was calibrated on a universe already several billion years into its chemical evolution, not on the universe's actual starting conditions. Untangling which one Webb had actually found meant looking closer, and one of the first places that closer look led was toward a population of galaxies unlike anything in the local universe. Astronomers would eventually give them a name that stuck for a reason: blue monsters. Push Webb's cameras out to a redshift greater than 10, astronomer shorthand, for looking at a period when the universe was younger than about 500 million years old, and a strange population starts showing up with unexpected regularity. This population entered the conversation almost immediately after the first deep-field images did. Researchers, including Rohan Naidu, began flagging candidate galaxies at these extreme redshifts within months of Webb opening its eyes in 2022, and it quickly became clear these weren't isolated flukes. As more of Webb's survey data came in, the count kept climbing, and it kept climbing well past what pre-Webb models of galaxy formation had forecast for this era. That on its own was the first surprise, not just that these galaxies existed, but that there were so many more of them than expected. These galaxies share a specific signature. They're extremely luminous in ultraviolet light. They're compact, often just a few hundred parsecs across, small enough that, dropped into our own galactic neighborhood, several of them would fit inside the gap between us and our nearest major stellar neighbors. And critically, their light is very blue, with almost none of the reddening that dust normally produces. That last detail is the one that stopped astronomers in their tracks. Dust matters enormously in galaxy studies because dust is a byproduct of stellar death. Heavier elements, carbon, silicon, the raw material of cosmic dust grains, are forged inside stars and scattered into space when those stars die. A galaxy needs at least one full generation of stars to live and die before it can build up any meaningful dust content. So a galaxy that's massive, luminous, obviously packed with stars, and yet almost completely free of dust looks like a contradiction. It looks like a galaxy that skipped a step it shouldn't have been able to skip. Researchers Francesco Zipparo, Andrea Ferrara, and colleagues formally proposed the name for this population, blue monsters, in a 2023 paper examining exactly this puzzle. Their galaxies showed stellar masses in the range of 100 million to 1 billion times the mass of our Sun, packed into that startlingly small volume, radiating with almost no dust attenuation at all. To put that compactness in perspective, a size of a few hundred parsecs is roughly 1,000 light-years across. Our own Milky Way, by comparison, stretches roughly 100,000 light-years from edge to edge. So picture a galaxy carrying the stellar mass of a small to mid-sized modern galaxy, but folded into a volume around 100 times smaller in diameter, densely packed, blazing bright, and by every measure available, almost entirely see-through where dust should be. These weren't rare, one-off oddities either. Once astronomers knew what to look for, blue monsters kept appearing across independent surveys, in numbers higher than pre-Webb models of the early universe had anticipated, not just one strange galaxy, but an entire, unexpectedly common category of them. Two competing explanations emerged, and this is important. Neither one requires abandoning the standard model of cosmology. The first possibility is that radiation pressure from newly formed, extremely hot stars is physically blasting the dust out of these galaxies almost as fast as it forms, before it has a chance to build up and redden the light. The second possibility is more subtle. The dust might still be there, but segregated, clumped in regions separate from the young, blue, star-forming regions Webb is actually detecting, so its reddening effect never shows up in the light we measure. Both remain active hypotheses. Neither has been fully confirmed. Some radio and submillimeter observations, using instruments like ALMA, the Atacama Large Millimeter Array, which can detect the glow of dust directly rather than just its dimming effect on starlight, have started testing which scenario fits better for specific galaxies. One frequently studied case. A blue monster catalogued as GHZ2 sitting at a redshift of roughly 12 showed no detectable dust emission at all in ALMA's follow-up observations, a result that favors the dust got ejected explanation for that particular galaxy, though it doesn't settle the question for the population as a whole. The honest answer, as of now, is that the debate is open, and it's the kind of open question that gets resolved one galaxy at a time, not with a single decisive paper. There's a third, more exotic idea that occasionally surfaces in this conversation. Worth mentioning precisely because it illustrates how far astronomers are willing to consider going when the standard explanations feel incomplete. The possibility that some of this extreme early light isn't coming from ordinary stars at all, but from massive, rapidly accreting black holes formed through processes we don't fully understand, yet sometimes called primordial black holes. This remains a minority position, explicitly speculative, and far less supported by current evidence than the dust-based explanations above. It's included here for one reason, to be transparent about where the genuine scientific frontier sits, versus where the debate has already narrowed to two well-supported possibilities. Here's what makes blue monsters worth sitting with, even without a final answer. They don't actually break cosmology, they complicate it. They suggest that star formation, dust production, and stellar feedback in the earliest environments the universe ever produced may simply operate by different rules than the versions we've built our intuition on, rules shaped by a universe that hadn't yet accumulated the heavier elements later generations would take for granted. That's one mystery. But less than a year after blue monsters entered the conversation, Webb turned up something else entirely, a population that looked less like an unusually efficient galaxy and more like something wearing a mask. They first appeared in Webb's data not long after the blue monsters did, small, compact, and unmistakably red, scattered across deep field images almost as soon as astronomers started combing through them in 2022. For a while, nobody had a formal name for them. They were just those little red things that kept turning up where they weren't expected. That changed in March 2024, when astronomer Jorrit Matthey and colleagues published a survey formally characterizing the population and giving it the name that's stuck ever since, little red dots. Their study, drawing on Webb's EIGER and FRESCO survey data, found these objects appearing in meaningful numbers starting around 600 million years after the Big Bang, and strangely, mostly disappearing from view again by around 1 billion years after the Big Bang, not rare stragglers. An entire population with what looks like a defined lifespan, confined to a specific window early in cosmic history. By 2025, researchers had cataloged 341 of them. Little red dots share a family resemblance with blue monsters, small, extremely distant, packed with more light than a galaxy that size and age should plausibly produce. But their color tells a different story. Where blue monsters are almost defiantly dust-free, little red dots show the opposite signature, a distinctive spectral shape, often described as V-shaped, consistent with something compact and heavily reddened. The leading explanation, developed across multiple studies through 2024 and reinforced by later spectroscopic work, points toward actively feeding black holes. Many little red dots appear to host a supermassive black hole in the process of rapidly pulling in surrounding gas. That infalling material doesn't fall in quietly. Friction heats it to extreme temperatures, and the result is intense light, radiating outward and swamping our view of the galaxy hosting it. From a distance of 12 or 13 billion light-years, a small galaxy with an unusually active black hole at its center can look, in terms of raw brightness, indistinguishable from a much larger galaxy simply packed with ordinary stars. Not every researcher reached for a black hole first. An alternative explanation put forward in 2024 by Julie Baggin and colleagues proposed that the distinctive light signature of little red dots, a sharp jump in brightness at a specific wavelength known as a Balmer break, might come from extremely dense, compact concentrations of ordinary stars. No black hole required. It's a real competing hypothesis, not a fringe one, and for a while it kept the black hole explanation from being the only story on the table. What tipped the balance was better spectra. A black hole actively swallowing gas leaves a specific fingerprint, broad, smeared-out emission lines, produced by gas whipping around the black hole at enormous velocities before it falls in. Dense star clusters don't produce that signature. Study after study through 2024 and into 2025 kept finding exactly that broad-line fingerprint in little red dot after little red dot, and by 2025, one gravitationally lensed example, an object called Glimpse 17775. Magnified by a foreground galaxy cluster acting as a natural lens, delivered the deepest spectrum of a little red dot ever recorded with more than 40 separate spectral lines, almost all of them consistent with the black hole-powered model. Researchers have started calling the underlying objects black hole stars, a deliberately strange name for a deliberately strange object, a supermassive black hole so thoroughly wrapped in the dense, glowing gas it's feeding on that the whole system radiates like a single, compact, star-like point of light. That distinction turned out to matter enormously for the original broken cosmology panic from Chapter 1. A study led by Catherine C.H. Worowski at the University of Texas at Austin, working with Stephen Finkelstein and collaborators, went back through the sample of impossibly massive early galaxies and asked a specific question: what happens to the too massive problem if you pull the little red dots out of the count? The answer was striking. Once black hole-dominated little red dots were removed from the analysis, the remaining galaxies fit comfortably within what the standard cosmological model predicts. As Finkelstein put it, there was no crisis in the underlying model of the universe after all. A theory that has survived decades of scrutiny didn't need to be thrown out. It needed a more careful accounting of what exactly was doing the shining. That should feel like a resolution. In a lot of ways, it is one, and it's worth pausing to appreciate how science actually looks when it's working. Not a single dramatic overturning of everything we thought we knew, but a population of galaxies getting quietly reclassified as researchers figured out what was really producing their light. But here's where it gets complicated again, and it's the detail most casual coverage leaves out. Even after removing every little red dot from the sample, roughly twice as many massive galaxies remained in Webb's early universe data than the standard model predicts. Not an overwhelming crisis, not a contradiction. Just a stubborn, moderate excess that black holes can't explain away, because these aren't black hole-dominated objects. They appear to be ordinary galaxies, simply forming stars somewhat faster, somewhat earlier than current models expect. One leading idea is that the early universe was more efficient at turning raw gas into stars than the universe is today, possibly because a denser, early cosmos made it harder for young stars to blow away their own fuel supply before finishing the job. So the mystery didn't disappear. It downgraded from "is the universe broken" to "why does star formation seem to run a little hotter than expected in the first billion years?" That's a real question, still being actively worked on, and still explicitly labeled as an open one rather than settled fact. One way to picture the leading idea: think about what stops star formation from running away with itself in a galaxy like ours. Gas cools, collapses under gravity, and starts forming stars, but as those stars form, they heat the surrounding gas back up, and that heat generates pressure pushing outward, slowing the whole process down. It's a built-in brake. In the early universe, though, everything was smaller, denser, and more tightly packed together. Some researchers now propose that in those conditions, the outward pushing pressure had a much harder time escaping the surrounding gas before more of it collapsed into stars, effectively loosening the brake and letting galaxies convert their raw material into stars faster than the same physics would allow today. It's sometimes described, informally, as feedback-free star formation, not because nothing pushes back, but because whatever pushes back doesn't manage to win the race in time. This remains an active area of research, tested against Webb's growing catalog of confirmed early galaxies rather than settled by any single study. And it turns out the little red dots and the leftover excess of massive galaxies aren't even the strangest thing Webb has found lurking in this era. Because while astronomers were busy explaining why some early galaxies looked too big, a completely different kind of anomaly was hiding in the data, not a galaxy that grew too fast, but one that had already, impossibly, finished growing altogether, stopped forming stars, stopped spinning. Gone still while the universe itself was barely out of its infancy. To be clear about what's confirmed and what isn't so far, the original broken cosmology, fear from Chapter 1, did not hold up as stated. Blue monsters remain genuinely puzzling, but don't require new physics, just a better understanding of dust and star formation in unfamiliar chemical conditions. Little red dots looked like a crisis and turned out, mostly, to be a population of black holes wearing a galaxy's mask. The residual excess of massive galaxies is real, moderate, and actively being investigated through star formation efficiency models, not evidence of anything broken. Every one of those threads gets picked back up later in this video, once we've laid out the strangest piece of the puzzle still to come. That's where we're headed next. By the end of the last part, the broken cosmology panic from 2022 had mostly cooled down. Blue monsters turned out to be a puzzle about dust, not a crisis about physics. Little red dots turned out to be black holes wearing a disguise, and even the leftover excess of massive galaxies had a plausible, non-catastrophic explanation waiting in the wings. None of that made the early universe boring. If anything, it made the remaining puzzles more interesting, because they were no longer competing with a false alarm for attention. Two threads were left hanging from part one, and a third hadn't even been introduced yet. This part picks up all three, starting with a single black hole that shouldn't have had time to grow this big. Behind a galaxy cluster called Abell 2744, itself a respectable 3 billion light-years away, sits something much farther out. A faint smudge of a galaxy named UHZ1, magnified by the cluster's gravity acting as a natural lens, turned out to be sitting at a redshift of about 10, roughly 13 billion light-years away, seen as it was when the universe was only about 3% of its current age, some 470 million years after the Big Bang. That lensing effect is worth pausing on, because it comes up more than once in this video. A sufficiently massive foreground object, in this case, an entire cluster of galaxies, bends the fabric of space around it enough to act like a crude, natural magnifying glass for anything sitting directly behind it from our point of view. Light from a background object gets bent, stretched, and brightened on its way to us, sometimes by a factor of several times its true brightness. Without that boost, many of the faintest, most distant objects in this video, UHZ1 included, would likely have stayed completely invisible, even to Webb. On its own, a galaxy that distant wouldn't be unusual news anymore by this point in the story. What made UHZ1 different is what astronomers found when they pointed the Chandra X-ray Observatory at it. After more than 2 weeks of accumulated observing time, an enormous investment for a single target, Chandra picked up a faint but unmistakable signal. X-rays, the telltale fingerprint of gas spiraling into a black hole and heating up to extreme temperatures on the way in. The source was classified as what astronomers call a Compton-thick quasar, meaning the black hole is so thoroughly wrapped in dense surrounding gas that even most of its own X-rays struggle to escape, only a faint fraction leaking through. Gravitational lensing from the foreground cluster boosted that already faint signal by roughly a factor of 4, which is the only reason it was detectable at all, even with 2 weeks of Chandra's undivided attention. The black hole itself, once the X-ray data was analyzed, turned out to weigh in at around 40 million solar masses. That number isn't the shocking part on its own. Black holes that size exist in plenty of present-day galaxies. The shocking part is the comparison. When researchers estimated the mass of the surrounding host galaxy using Webb's infrared data, they found something that essentially never happens in the universe as we currently know it. The black hole's mass and the galaxy's stellar mass came out roughly comparable to each other. In our own galactic neighborhood, a supermassive black hole typically makes up something like 0.1% of its host galaxy's total stellar mass. The black hole is the small, dense passenger. The galaxy is the vehicle. In UHZ1, the passenger weighs about as much as the vehicle. A concrete comparison helps here. Sagittarius A star, the supermassive black hole sitting at the center of our own galaxy, weighs in at a little over 4 million solar masses, itself a genuinely enormous object, but one that amounts to a tiny fraction of the Milky, weighs roughly 60 billion solar masses of stars. UHZ1's black hole is about 10 times heavier than Sagittarius A star in raw terms, while its host galaxy appears to have barely begun assembling any stellar population at all. Scale a black hole like ours up by a factor of 10 and shrink its host galaxy down by a factor of thousands, and you'd land somewhere close to what UHZ1 actually looks like. That's not a small discrepancy to explain away, and it isn't the kind of measurement error that better data quietly resolves. It points toward a specific, competing idea about how the first black holes in the universe actually got started, a question that's been open for longer than Webb has existed. There are two broad camps. The first, sometimes called the light seed scenario, proposes that the earliest black holes started small, as the collapsed remnant of a single massive first-generation star, something in the range of 100 solar masses, and then grew larger over time by steadily pulling in gas and merging with other black holes. It's a conservative picture, built entirely out of physics we've already tested. The problem is timing. Growing a black hole from 100 solar masses up to something like UHZ1's 40 million in less than 500 million years requires accretion rates running close to the theoretical maximum for almost the entire time available. The Eddington limit, the point at which the outward pressure of a black hole's own radiation starts pushing infalling gas away as fast as gravity pulls it in. Sustaining growth that close to that ceiling, continuously, for hundreds of millions of years without interruption, is not impossible, but it leaves very little room for anything to go differently. The second camp, the heavy seed scenario, proposes a shortcut, instead of forming a star first and collapsing it later. An enormous pristine cloud of primordial gas, one massive enough and free enough of the complicating heavier elements later generations of stars would produce, could collapse directly into a black hole, skipping the star phase entirely. That direct collapse could plausibly produce an initial seed already weighing tens of thousands of solar masses, giving it a massive head start toward the kind of numbers UHZ1 displays, without ever needing to sustain years of uninterrupted maximum rate feeding. This isn't a new idea invented to explain UHZ1. Astrophysicist Priyamvada Natarajan had described the theoretical profile of what she called an outsized black hole galaxy back in 2017, years before Webb had even launched, predicting the specific combination of properties that would show up if direct collapse seeding were real. An early galaxy with an unusually massive X-ray bright black hole, roughly matching its host galaxy's own stellar mass, likely showing signs of a recent merger. When the Chandra and Webb data on UHZ1 came back, in a study led by Natarajan alongside Akos Bigdan and colleagues, published in December 2023, the match to that 8-year-old prediction was, in the author's own description, striking. UHZ1 remains the leading real-world candidate for a black hole born heavy from the start, rather than one that grew into its size the slow way. This isn't the end of the story on early black hole growth. It's a data point in an active, ongoing debate. But it's a rare case where a theoretical prediction, made years in advance without any specific galaxy in mind, was later matched almost point for point by an actual observation. UHZ1 also isn't alone anymore. In December 2024, a separate team led by Ignaz Juhas at the University of Cambridge reported a second overmassive black hole in a galaxy catalogued as GN 1001830, seen about 800 million years after the Big Bang. This black hole weighed in at roughly 400 million solar masses, about 40% of its host galaxy's entire stellar mass, something like 1,000 times above the typical ratio seen in the nearby universe. But the detail that made this discovery particularly useful wasn't just its size. It was how quietly it was feeding. The data showed this black hole accreting gas at only about 2% of its theoretical maximum rate. It wasn't in the middle of a growth spurt. It was resting. That single detail helps resolve part of the timing problem raised earlier. If black holes in the early universe don't grow at a steady, moderate pace, but instead alternate between short, extreme bursts of near maximum accretion and much longer stretches of near total dormancy, then reaching an enormous mass within a few hundred million years, becomes easier to explain without requiring implausibly sustained feeding rates the entire time. A black hole could spend most of its early life quietly, napping, as several astronomers have described it, punctuated by brief windows of explosive growth, and still end up looking overmassive whenever Webb happens to catch it. GN 1001830 doesn't replace the direct collapse explanation for UHZ1. It adds a second, complementary piece to the puzzle, not just how a black hole might start out heavy, but how it might grow the rest of the way without breaking any known physics. Between the two of them, UHZ1 and GN 1001830 leave one question conspicuously open. If some early black holes really did start out heavy, born from direct collapse rather than a dying star, what would that collapsing material have looked like right before it became a black hole? One genuinely speculative answer to that question is waiting a few chapters ahead in this video. First, though, there's a different kind of anomaly to deal with, because while astronomers were reclassifying little red dots and puzzling over black holes that arrived too early, an entirely different discovery was complicating the picture from the opposite direction, not too bright and dust-free, but too massive and buried in dust that by every existing model shouldn't have had time to form. Dust has been a recurring character in this video, and for good reason. It's the single ingredient that keeps showing up in the wrong place at the wrong time. Blue monsters were strange because they had none of it when they should have had some. The next population Webb turned up is strange for exactly the opposite reason. Massive galaxies, less than 1 billion years after the Big Bang, wrapped in so much dust that earlier telescopes, working in visible and ultraviolet light, couldn't see them at all. This is precisely the kind of population Webb was built to find, and older telescopes were structurally blind too. Dust absorbs and scatters shorter, bluer wavelengths of light far more effectively than longer, redder ones, which is exactly why sunsets on Earth look red, as dust and air molecules scatter away the blue light and let the red light through. A galaxy wrapped in enough dust doesn't just look reddish. In visible and ultraviolet light, it can effectively disappear, its starlight scattered and absorbed into invisibility. Webb's infrared instruments see straight through that veil, picking up the reprocessed glow the dust re-emits at longer wavelengths instead. In November 2024, a team led by Menjuan Zhao and Pascal Ish at the University of Geneva published results from the FRESCO survey, which had systematically searched for galaxies with a particular kind of emission line signature indicating heavy dust content. Out of 36 candidate galaxies flagged this way, most fit comfortably within existing models. 3 did not. Those 3, found within the first billion years after the Big Bang, turned out to carry stellar masses comparable to, in some cases exceeding, our own Milky Way's more than 100 billion solar masses. And they were forming new stars roughly 2 to 3 times more efficiently than typical galaxies from the same era, or than ordinary galaxies form stars even today. Their heavy dust content gave them a distinctly red appearance in Webb's images, and the team gave them the name that stuck, red monsters. To put that efficiency number in context, galaxies today typically convert somewhere around 1/5 of their available gas into stars over their lifetime, with the rest either staying as unused gas or eventually blown away entirely. A galaxy converting gas into stars 2 to 3 times faster than that isn't a minor statistical outlier. It's operating close to whatever physical ceiling exists on how quickly star formation can proceed at all. Researcher David Elbaz, commenting on the discovery, noted that these galaxies true Massive nature had been essentially invisible before Webb hidden by exactly the dust attenuation that makes them red monsters in the first place, a population that pre-Webb telescopes weren't just missing by chance, but were structurally incapable of detecting. The problem these three galaxies posed wasn't just their existence, it was the arithmetic of how a galaxy accumulates dust in the first place. As established earlier in this video, dust comes from dying stars, heavier elements forged in stellar interiors, scattered into space when those stars reach the end of their lives. Building up enough dust to visibly redden an entire massive galaxy isn't instantaneous. It requires generations of star formation and stellar death to have already happened. Finding that much dust already in place within the universe's first billion years meant these galaxies had somehow compressed several cycles of stellar birth and death into a fraction of the time such cycles were assumed to need. Then, within roughly a year, the picture pushed even further back. A preprint study led by Giulia Rodig identified a single galaxy, cataloged as EGSZ11R0, showing the same dusty, massive signature, but at a redshift corresponding to roughly 400 to 500 million years after the Big Bang, nearly as early as the blue monsters themselves. This result had not yet completed peer review at the time of writing, so it's presented here explicitly as a preliminary finding rather than a settled fact. What made this particular case compelling enough to report on despite its preprint status was the depth of the supporting evidence. Rather than relying solely on color and brightness, the team obtained a full spectrum of the galaxy, splitting its light apart wavelength by wavelength. Buried in that spectrum, they identified a signature associated with carbon, a heavier element that, like dust itself, can only exist because at least one earlier generation of stars already lived, fused it in their cores, and died, scattering it into the surrounding gas. Finding carbon this early adds an independent line of evidence, on top of the dust itself, that this galaxy had already completed more than one full cycle of star formation and stellar death, compressed into a few hundred million years. Astrophysicist Pieter van Dokkum, who wasn't involved in the study, described the short timescale involved as genuinely surprising, while other outside reviewers characterized the analysis extracting these signatures as an impressive technical achievement in its own right. If it holds up under further scrutiny, EGSZ11R0 would mean dust-obscured, chemically mature. Massive galaxies existed almost as early as the dust-free ones, two seemingly opposite populations occupying almost the same narrow slice of cosmic history. Rodig and her team have proposed a way these two extremes might actually be connected rather than contradictory. A red monster and a blue monster could be the same object, seen at two different moments. In this picture, a galaxy goes through an intense, compressed burst of star formation and dust production first, appearing red and dust-choked. Then, as radiation pressure from all those newly formed stars builds up, it eventually blows the dust clear, revealing the same galaxy's young, blue stellar population underneath, the blue monster phase arriving as what's left after the dust clears out. It's an elegant hypothesis specifically because it turns two separate mysteries into two snapshots of a single process, governed by the same underlying mechanism proposed earlier in this video to explain how blue monsters lose their dust in the first place, radiation pressure clearing the way. It has not been confirmed, and confirming it isn't a simple matter of finding one more example of either type. What it would actually require is catching individual galaxies at intermediate stages, objects visibly in the middle of transitioning, showing some regions still dust-choked and others already cleared, or showing a declining dust signature correlated with an aging stellar population. That kind of evidence takes both a large enough survey to catch a galaxy at the right transitional moment, and spectroscopy detailed enough to measure dust and stellar age simultaneously in the same object. It's a testable idea, in other words, but the test itself is demanding, and nobody has run it conclusively yet. Either way, red monsters extend the same lesson blue monsters and little red dots already taught. The early universe was not simply a slower, smaller-scale rehearsal for the universe we see today. It appears to have run several of its formative processes, star formation, dust production, black hole growth, on a faster, more compressed timeline than intuition, calibrated on a much older universe, would ever have predicted. That leaves one thread still untouched, the strangest, and most explicitly speculative of the entire video. It circles back to the black hole seeding puzzle from the start of this part, and it starts with a very simple, very strange question. What if some of Webb's earliest galaxies aren't galaxies at all? Every explanation so far in this video, however strange, has kept one assumption intact, that the light Webb is collecting comes from galaxies, collections of ordinary stars and gas, however unusually massive, however unusually bright, however unusually organized. There is one hypothesis on the table that abandons even that assumption. The idea predates Webb by more than a decade. In 2007, physicists Douglas Spaliar, Catherine Fries, and Paolo Gondolo proposed that the very first stars in the universe might not have been powered by nuclear fusion at all, at least not at first. Instead, in regions of the early universe dense enough with dark matter, that dark matter could collect at the center of a forming protostar and begin annihilating, releasing heat. If that heating process were efficient enough, it could hold the star up against gravitational collapse without any fusion happening at its core, essentially a star running on an entirely different engine. They called the resulting object a dark star, borrowing the name, by Fries's own account, from the Grateful Dead song of the same title. It's worth being clear about what a dark star would and wouldn't be made of, because the name invites confusion. A dark star isn't made of dark matter itself. It's built almost entirely from the same ordinary hydrogen and helium as any other early star, gas left over directly from the Big Bang. Dark matter's role is purely as a heat source, gathering densely enough at the star's core for its self-annihilation to outshine, temporarily, the energy that fusion would otherwise provide. Because that heating mechanism doesn't depend on building up enough core pressure and temperature to ignite fusion, a dark star can theoretically balloon to sizes and luminosities that would tear an ordinary star apart, so long as fresh dark matter keeps flowing in to fuel it. The theoretical properties of a dark star, if one could form and survive, are extreme even by the standards of this video. Fed by a large enough dark matter halo models, suggest these objects could grow to roughly 1 million to 10 million times the mass of our Sun. Radiating with up to 10 billion times the Sun's luminosity, a single object bright enough to rival an entire ordinary galaxy while remaining physically a single star. For over a decade, this remained a purely theoretical proposal, with no way to test it against actual data. That changed once Webb started returning spectra of the earliest confirmed light sources in the universe. In 2023, Cosmin Illy Gillian Paulin and Catherine Fries published an analysis in the Proceedings of the National Academy of Sciences, identifying 3 objects, originally catalogued as ordinary galaxies by the JWST survey in December 2022, named JWST GSZ 11-0, JWST GSZ 12-0. and JADS GS-Z13-0, whose photometric properties were consistent with a dark star interpretation rather than a conventional galaxy of many stars. The key piece of evidence was that these light sources appeared unresolved. Whatever was producing the light was small enough and simple enough in structure to be compatible with a single object rather than a sprawling collection of millions of stars. A follow-up spectroscopic study extended the search, and this is where the story loops back to a name already familiar from earlier in this video. Alongside two of the original candidates, researchers identified two additional dark star candidates, JADS GSZ14-0, and a companion object, JADS GSZ14-1. JADS GSZ14-0 is the same record-breaking galaxy introduced in part 1 of this video, the confirmed redshift 14, object that Stefano Carniani's team had already flagged as stunningly massive and luminous for its age. According to this analysis, its spectrum contains a specific feature, an absorption line from ionized helium at a wavelength of 1640 angstroms, that the authors describe as a distinguishing signature theoretically expected from a dark star, and not from an ordinary population of galaxy stars. The reasoning behind treating that particular absorption line as a meaningful test is worth unpacking briefly. In an ordinary galaxy built from millions of individual stars, the combined light gets smoothed out, averaged across stars of many different ages, temperatures, and compositions, which tends to wash out sharp, specific spectral features. A single, enormous dark star, by contrast, would have one very particular surface temperature and composition, predicted fairly precisely by the underlying dark matter-powered stellar models. That specificity is what makes the predicted helium absorption line useful as a test. It's not a feature astronomers went looking for after the fact, but one calculated in advance from the theory, then checked against the data. It's worth being precise about what that does and doesn't mean. It does not mean JADS GSZ14-0 has been confirmed as a dark star instead of a galaxy. The helium absorption feature is described by its own authors as a candidate signature, one piece of suggestive spectroscopic evidence. Not a definitive identification, and it sits inside a single research group's ongoing work, not yet independently replicated by competing teams the way the little red dot black hole explanation eventually was. The conventional interpretation, an unusually massive, unusually efficient galaxy of ordinary population III stars, remains the mainstream explanation for these objects, including JADS GSZ14-0, among the broader astronomical community. Part of that caution comes down to a simple point of parsimony, a compact cluster of many faint hot. Metal-free stars can in principle mimic several of the same broad photometric signals a dark star would produce without requiring a new form of stellar physics or a specific dense concentration of dark matter to already be in place at exactly the right location and time. Extraordinary claims, in other words, are being held to a correspondingly high standard of evidence, which is exactly how this stage of the scientific process is supposed to work. What makes the dark star hypothesis worth including in this video, despite its speculative status, is what it would explain if it turned out to be right. Catherine Fries and her colleagues have specifically proposed dark stars as a possible missing link in the black hole seeding puzzle raised earlier in this part. A dark star, once its dark matter fuel source runs out, wouldn't simply fade away. Models suggest it would collapse directly into a black hole, and depending on how massive the dark star grew first, that collapse could hand a young universe a black hole seed already weighing tens of thousands or more solar masses. That's the exact kind of head start the heavy seed explanation for objects like UHZ1 requires, arrived at from a completely different direction, through a hypothesis about the nature of the first stars rather than a direct study of black hole demographics. There's a second reason this hypothesis draws serious attention, beyond its tidy connection to black hole seeding. Dark stars would be, for the moment, the only proposed astrophysical object whose observation could provide direct evidence for dark matter's existence beyond its gravitational effects. Every other line of evidence for dark matter, galaxy rotation curves, gravitational lensing, the large-scale structure of the universe, infers its presence indirectly, through how its gravity shapes the motion and arrangement of ordinary matter. A confirmed dark star would be different, a case where dark matter wasn't just tugging on things gravitationally from the shadows, but actively powering a visible, observable object through a completely different physical process, annihilation rather than gravity. That's a large part of why a still unconfirmed hypothesis, resting on a handful of candidate objects and one debated spectral line, continues to draw serious attention from working physicists rather than being dismissed outright. None of that makes dark stars confirmed. It makes them a genuinely open, testable hypothesis, sitting at the edge of current evidence, with a specific, falsifiable prediction attached to it. Future, deeper spectra of these candidate objects, and others like them, should eventually confirm or rule out the helium signature the theory predicts. That's a real scientific position to be in, not proven, not dismissed, waiting on more data that Webb is actively capable of collecting. Step back for a moment from any single object in this part, and a pattern starts to emerge across all three chapters. UHZ1 and GN1001830 suggest the earliest black holes may have arrived already heavy, or grown in violent, irregular bursts rather than at a slow, steady pace. Red monsters suggest galaxies compressed multiple full cycles of star birth and death into a fraction of the time such cycles are assumed to require. Dark stars, if they're real, suggest the very first generation of luminous objects in the universe might not have been ordinary stars at all. Three completely independent lines of evidence, three different teams, three different kinds of data, and all three point toward the same broad conclusion. Whatever rules governed the first billion years of cosmic history, they allowed things to happen faster and stranger than a straightforward extrapolation from the universe we live in today would predict. Between an overmassive black hole that shouldn't have had time to grow two populations of monster galaxies pulling in opposite directions on the question of dust, and a hypothesis that some of the universe's first light might not be coming from stars in the conventional sense at all, the early universe Webb has revealed looks less like a simplified preview of the cosmos we know, and more like a chapter of cosmic history that ran by its own faster, stranger rules. But everything covered so far, however extreme, has still been about galaxies and objects that grew too fast, too early, too bright. The next part turns to something that breaks the pattern in the opposite direction entirely. Not a galaxy caught growing up too quickly, but one that had already completely stopped. Everything covered so far in this video has been a variation on the same basic surprise. Something in the early universe grew too fast, got too bright, or got too massive too soon. An overmassive black hole. Two populations of monster galaxies pulling in opposite directions on the question of dust. A speculative hypothesis about starlight that might not come from stars at all. All of it, one way or another, has been about excess, too much, too early. This part is about the opposite kind of impossible, not a galaxy that grew too fast, a galaxy that finished, completely, while the universe itself was barely out of its infancy, if the first two parts of this video were about things arriving ahead of schedule. This part is about something reaching the end of its schedule ahead of time, a distinction that turns out to matter because growing fast and dying young are different puzzles requiring different explanations. Even though both point toward the same broader conclusion about how compressed the early universe's timeline for galaxy evolution really was. Start with the numbers, because they need to be sitting clearly in view before the rest of this chapter makes sense. The object is called XMM Vid-1 2075. It sits roughly 12 billion light-years away. We're seeing it as it existed roughly 1 billion years after the Big Bang, when the universe, currently 13 billion years old, was younger than 1/7 of its current age. It carries several times as many stars as our own Milky Way. And according to a paper published in Nature Astronomy on May 4, 2026, led by research scientist Ben Forrest at the University of California, Davis, it is almost certainly not rotating at all. This particular galaxy didn't come out of nowhere, since Webb's earliest surveys. Astronomers have steadily built up a catalog of massive galaxies that had already shut down star formation earlier in cosmic history than standard models expected, a population sometimes described a little informally as red and dead. Red because without new blue hot young stars being formed. A galaxy's light skews toward the older redder stars already present dead, because star formation itself has effectively stopped. This fits inside a broader, well-established pattern astronomers call cosmic downsizing. Across the history of the universe, the most massive galaxies tend to finish forming their stars first, while smaller galaxies keep forming stars for much longer. It's counterintuitive at first, since bigger usually implies took longer to build, but the observed pattern runs the other way. Mass assembles fast at the high end, then shuts off early, while smaller galaxies simmer along for billions of additional years. Downsizing itself isn't new or controversial. It's been documented since long before Webb existed. What Webb has done is push the earliest confirmed examples of it back much further than anyone expected, into a period when, by the standard timeline, massive galaxies should have barely finished assembling, let alone already finished quenching. As early as 2023, a study led by Adam Carnall, using some of Webb's first deep field data, reported finding these massive quiescent galaxies roughly an order of magnitude, something like 10 times, more often than existing galaxy formation models predicted for this era of cosmic history. That same team went on to spectroscopically confirm one particularly striking example, a galaxy called GS 9209, already quiescent just 1 billion years after the Big Bang. The puzzle, in other words, wasn't limited to a single unusual object. It was a statistical excess, showing up across independent surveys of galaxies that had already finished the job of forming their stars far earlier and far more often than theory expected. XMM Vid-1 2075 belongs to that broader population. What makes it a chapter of its own? Rather than just one more entry in that catalog, is the specific additional detail Forrest's team was able to measure this time, not just that the galaxy had stopped forming stars, but that its internal structure looked like it belonged to a galaxy many billions of years older than it actually is. To understand why that last detail is the one that matters, it helps to know what not rotating actually means for a galaxy, and why it's supposed to take an enormously long time to get there. Picture two very different ways a large group of stars can hold itself together against the pull of its own gravity. The first way is rotation, stars orbiting a common center in roughly the same direction, the way planets orbit the sun, the the way the Milky Way's own disk spins once every couple 100 million years. That's the arrangement young, actively star-forming galaxies typically have, because gas naturally settles into a rotating disk as it collapses, and new stars form directly out of that spinning material, inheriting its orderly motion. The second way is what astronomers call dispersion-supported motion, stars moving in essentially random directions. Held up against collapse not by orderly orbital motion, but by the sheer chaos of that motion, the same way a swarm of bees stays aloft through constant disordered movement, rather than any single coordinated flight path. Each individual insect's motion looking arbitrary, while the swarm as a whole holds together. This is the structure seen in giant elliptical galaxies in the present-day, nearby universe, and those galaxies didn't start out that way. They earned that chaotic structure, according to standard theory, through billions of years of galactic mergers. Each collision between two rotating galaxies scrambles their combined orbital motion a little more, and after enough mergers, spread across enough cosmic time, the orderly spin gets ground down into disorganized, random motion. It's less like a single event and more like erosion, repeated over billions of years, wearing down or the way water gradually wears down rock. That's why XMM Vid 1 2075 is such a strange find. Forrest's team wasn't looking at it for the first time. It had already been flagged, years earlier, by the MAGA-Z3NE survey, massive ancient galaxies at Z greater than 3 near-infrared, using ground-based observations from the W.M. Keck Observatory in Hawaii. That earlier work had already established two things about this galaxy. It was genuinely one of the most massive galaxies known from this era of cosmic history, and it had already stopped forming new stars entirely. Its star formation rate having fallen to less than 1 solar mass per year. For comparison, the Milky Way, despite being a fairly ordinary, unremarkable galaxy, by today's standards, still forms roughly 1 to 2 solar masses of new stars every year. XMM Vid 1 2075, several times more massive than the Milky Way, had essentially gone quiet. That combination, already enormous, already finished forming stars, made it a natural target for a more detailed follow-up. Forrest's team used Webb's NIRSpec instrument, configured as an integral field unit, capable of capturing a full spectrum at every individual point across the galaxy's image, rather than just one averaged spectrum for the whole object, to measure the actual motion of material inside XMM Vid 1 2075 directly. The difference this makes is a bit like the difference between recording an entire choir with a single microphone versus giving every singer their own. A single averaged spectrum can only tell you the overall blend of motion across a galaxy, useful but blurry. An integral field spectrum measures the light, and therefore the velocity coming from dozens of separate points across the galaxy's face, independently making it possible to actually map out which regions are approaching, which are receding, and whether that pattern traces the smooth, organized signature of rotation or the scattered, directionless signature of chaos. They ran the same measurement on two other massive galaxies of comparable age as a point of comparison. One of the three showed clear, orderly rotation, behaving the way theory expects an actively assembling galaxy to behave. A second showed messier, partially disordered motion, a plausible intermediate case. XMM Vid 1 2075 showed no coherent rotation signal at all. Its stars were moving in what looked like essentially random directions, the same disordered, dispersion-supported structure normally reserved for ancient elliptical galaxies that have had 10 billion years and countless mergers to arrange themselves that way. It's worth being upfront about the size of that comparison sample. 3 galaxies is not, on its own, enough to establish a population statistic. One rotator, one intermediate case, and one clear non-rotator, out of a sample of 3, doesn't tell you what fraction of all massive early galaxies eventually end up in this dispersion-supported state. What it does establish, credibly, is existence, proof that this specific structural endpoint, previously assumed to require most of cosmic history to reach, could genuinely be achieved within the universe's first 2 billion years. Confirming how common that outcome actually is will require expanding this kind of detailed kinematic study to many more galaxies, which is exactly the kind of follow-up work Forrest's team has flagged as the natural next step. It's worth sitting with how strange that timing actually is. The standard explanation for how a galaxy loses its rotation, repeated mergers, grinding down orbital motion over cosmic ages, assumes a process measured in many billions of years. XMM Vid-1 2075 had less than 2 billion years of total cosmic history available to it, and some fraction of that time simply had to be spent forming the galaxy's stars in the first place, before any merger-driven scrambling could even begin. The arithmetic doesn't obviously work if the standard, slow, many mergers explanation is the only mechanism in play. Forrest and his team have proposed an alternative that doesn't require billions of years of gradual erosion, not a long history of multiple mergers, but a single, violent, close-to-head-on collision between 2 galaxies that happen to be rotating in close to opposite directions from each other. Think of 2 spinning tops, each rotating smoothly and independently, suddenly colliding directly into one another. 2 rotating disks colliding at a gentle angle, spinning the same general direction, would likely combine into a single larger disk that keeps spinning, its motion mostly preserved. But 2 disks colliding almost head-on, spinning in close to opposite directions, would have their orbital motions actively working against each other at the moment of impact, one system's clockwise motion canceling against the other's counterclockwise motion, rather than reinforcing it. Run that scenario forward, and the math changes considerably. 2 organized rotating systems colliding almost directly with their opposing spins, working against rather than reinforcing each other, could plausibly cancel out most of their combined orbital motion in a single event, one dramatic collision doing in one shot what would otherwise require a long sequence of smaller mergers spread across cosmic time. The team's kinematic data is consistent with this scenario, though, and this matters, it isn't the only galaxy in the early universe caught in a similarly disordered, chaotic-looking state. It fits a broader, still-developing picture, rather than standing as an isolated, fully explained oddity. What XMM Vid-1 2075 represents, then, isn't a violation of physics. Nothing about a single massive collision breaks any established law. What it represents is a shortcut, a route to the same structural endpoint that billions of years of gradual accumulation normally produce, compressed instead into a single dramatic event, early enough in cosmic history that the result looks on paper like it shouldn't have had time to exist yet. A galaxy that finished the job that giant ellipticals normally take 10 billion years to complete in under 2. Go back for a moment to the very first thing said in this video. One galaxy in the early universe had already stopped growing, stopped spinning, stopped making stars altogether, less than 2 billion years after the Big Bang. That description wasn't a composite or a simplification for the sake of a dramatic opening line. It was XMM Vid-1 2075, described exactly as Ben Forrest's team found it. Everything covered in the chapters since then, the little red dots, the blue and red monsters, the overmassive black holes, even the speculative dark stars, has been building toward this same galaxy, approached from a dozen different angles. This is the object this entire video has been circling. That leaves one more piece of this particular puzzle unaddressed, and it's the piece that connects XMM Vid1 2075 to a much bigger pattern running through Webb's entire catalog of early universe discoveries. This galaxy isn't alone. Massive, already quiescent galaxies keep turning up earlier than models predict, again and again, across independent surveys. The same statistical excess Carnall's team first flagged back in 2023. A merger can explain why a galaxy stops spinning. It doesn't, on its own, explain why so many massive early galaxies stop forming stars in the first place. Sometimes, as with XMM Vid1 2075, well before the universe has even reached its second billionth birthday. For that half of the puzzle, a separate piece of very recent research offers what might be the clearest direct evidence yet. If XMM Vid1 2075 is the finished product, a galaxy caught long after whatever killed its star formation had already run its course, its history, reconstructed only indirectly. After the fact, the galaxy at the center of this chapter is something rarer and in some ways more valuable to astronomers, one caught in the act mid-process with the actual mechanism still visibly operating in real time. It's called CRISTAL-02, and it's one entry in a larger effort called the CRISTAL survey, an acronym for CII resolved ISM in star-forming galaxies with ALMA. The survey uses the Atacama Large Millimeter Array in Chile combined with Webb and Hubble imaging to study the internal structure of dozens of star-forming galaxies as they appeared roughly 1 billion years after the Big Bang, tracking a specific wavelength of light, 158 microns, emitted by ionized carbon, that traces the location and motion of a galaxy's cold gas reservoir directly. That particular tracer matters for a practical reason. Cold gas, the actual raw material available for future star formation, doesn't glow brightly in visible or even most infrared light. Ionized carbon emission at this specific wavelength is one of the few signals bright enough, at these enormous distances, to map where a galaxy's gas is located and, crucially, which direction it's moving, inward, settling into future stars or outward, escaping the galaxy entirely. In June 2026, a team led by astrophysicist Rebecca Davies at Swinburne University of Technology in Australia published a detailed analysis of one particular galaxy from that survey, CRISTAL-02, in the monthly notices of the Royal Astronomical Society. At the time this light left its source, CRISTAL-02 was forming stars at a genuinely furious pace, around 260 solar masses of new stars every year, roughly 3 times faster than a typical galaxy of its mass and age, placing it firmly in what astronomers call a starburst phase. That alone wouldn't be especially remarkable. Starburst galaxies, brief periods of unusually intense star formation, show up throughout cosmic history, in the present-day universe as well as the distant past. What made CRISTAL-02 worth a dedicated study was what the team found surrounding it, an enormous plume of cold gas, extending outward from the galaxy across a distance almost as long as the galaxy itself. That plume is the signature of an outflow, material being actively blown out of the galaxy rather than sitting quietly within it. And when the team measured how much material that outflow was actually carrying, the number was startling, roughly 520 solar masses of gas per year. Exiting the galaxy, about twice the rate at which the galaxy was simultaneously forming new stars and roughly 20 times faster than the typical outflow rate measured in other massive galaxies from the same era of cosmic history. Here's why that ejection rate matters so much. Gas is the raw fuel for star formation. No gas, no new stars, regardless of how much a galaxy might otherwise want to keep growing. Astronomers have a specific term for a galaxy shutting down star formation this way: quenching. It's a useful word precisely because it's mechanism neutral. It describes the outcome, a galaxy going quiet, without presupposing which process caused it. A galaxy losing gas twice as fast as it's converting that same gas into stars is running a fuel deficit it cannot sustain. Run the numbers forward at the rates observed, and the team's analysis suggests CRISTAL-02 would exhaust its remaining reservoir of star-forming gas in less than 100 million years, a brief window by any cosmic measure. And one that would leave behind exactly the kind of object this video has spent the last several chapters puzzling over: a massive, suddenly quiescent galaxy, its star formation switched off. At a point in cosmic history when the universe had barely had time to build such a galaxy in the first place. What's driving that wind matters as much as the wind itself, because it determines how widely this explanation can be applied. There are two broad candidates for what powers a galaxy-scale outflow like this. The first is feedback from an actively accreting supermassive black hole, energy and radiation pressure from material falling toward a central black hole, powerful enough to blast surrounding gas outward. This mechanism, sometimes called AGN feedback, has a long track record in galaxy formation theory, specifically because it scales so well. A supermassive black hole accreting near its theoretical maximum rate can output more energy than the combined light of every star in its host galaxy, more than enough in principle to sweep gas out of an entire galaxy at once. Prior simulations had generally assumed that black hole-driven feedback was necessary to produce outflows forceful enough to fully shut down star formation in a galaxy this massive. Stellar processes alone, in most models, simply weren't expected to pack enough punch. The second candidate is exactly that stellar process: the combined force of stellar winds and especially supernova explosions, the deaths of the most massive, short-lived stars formed during the current starburst, each one releasing a violent shockwave into the surrounding gas. Davies and her team's analysis points toward the second option. The physical mechanism behind a supernova-driven wind is, at its core, fairly intuitive. When a star many times more massive than the Sun reaches the end of its life, it doesn't fade quietly, it detonates, releasing a shockwave of energy and debris into the surrounding gas. One supernova is a local event, but a starburst, by definition, produces a large number of massive, short-lived stars in a short span of time, all forming together and all dying together, on a stellar timescale of just a few million years. Concentrate enough of those explosions close together in both space and time, and their combined shockwaves can merge into something bigger than any single blast: a coordinated, galaxy-scale wind, sweeping outward through the surrounding gas and carrying a meaningful fraction of it entirely out of the galaxy. The evidence for this mechanism, specifically, comes from where, within CRISTAL-02, the outflow originates. CRISTAL-02 isn't a single smooth structure. It's made up of several distinct clumps of material, and the clump most directly associated with the outflow shows a noticeably younger stellar population and a higher current star formation rate than the other clumps in the galaxy. That's the fingerprint of a supernova-driven wind specifically. A recent concentrated burst of star formation, followed shortly after by the deaths of the most massive stars in that burst, unleashing a wave of supernova explosions, concentrated in both space and time, powerful enough collectively to drive gas out of the galaxy without necessarily requiring any black hole involvement at all. This is presented as evidence, not certainty, and the researchers were careful to say so themselves. They cannot fully rule out a black hole contribution. It's possible CRISTAL-02 hosts a supermassive black hole that simply wasn't actively accreting, and therefore invisible at the specific moment Webb observed it. That possibility should sound familiar. It's the same basic scenario encountered earlier in this video with GN 1001830. The napping black hole from Part 2. A supermassive black hole can sit quietly undetectable by its light output for long stretches of time, even while remaining fully capable of driving powerful feedback whenever it does become active. A dormant black hole in CRISTAL-02 wouldn't necessarily show up in the data at all, which is exactly why the researchers frame their supernova-driven explanation as the best supported option given current evidence, rather than the only option logically available. Distinguishing between the two scenarios matters for a reason beyond simple curiosity. The two mechanisms behave differently over time. A supernova-driven wind is inherently temporary. It fades once the triggering burst of star formation itself winds down, because no new supernovae means no new push. A black hole-driven wind, by contrast, can persist for as long as the black hole keeps actively feeding, potentially hundreds of millions of years, which matters enormously for whether a galaxy's shutdown turns out to be permanent or merely a temporary pause before gas eventually flows back in and star formation resumes. To test whether CRISTAL-02 represents a genuine common mechanism rather than an isolated fluke, Davies' team compared its outflow properties against a much larger sample. 99 separately measured galactic outflows spanning roughly 12 billion years of cosmic history. From the nearby universe all the way back to the earliest galaxies Webb can currently observe. Building that comparison sample meant pulling together outflow measurements from many separate studies, conducted by different teams using different instruments and techniques across more than a decade of research, and placing them all on a common scale so that a fair comparison could actually be made. The result was that the underlying relationship between a galaxy's properties and how efficiently it drives gas outward has stayed roughly consistent across that entire span of cosmic time. The physics of outflows doesn't appear to be fundamentally different in the early universe. What differs is simply how often galaxies experience the extreme conditions, rapid mergers, tightly concentrated starbursts, able to trigger an outflow this violent. And extreme conditions, it turns out, were considerably more common in the crowded, actively assembling early universe than they are today. Current estimates suggest close to half of all massive galaxies in this era of cosmic history are actively interacting or merging with a nearby neighbor at any given time. Compared to a much smaller fraction of galaxies undergoing major mergers in the present-day comparatively settled universe. That last point is what elevates CRISTAL-02 from an interesting single case study into something closer to a general explanation. Recall the number from earlier in this part. Carnell's 2023 survey found massive quiescent galaxies showing up roughly 10 times more often than standard models predicted for this era of cosmic history. A tenfold excess is exactly the kind of gap that needs a correspondingly common mechanism to close it, not a rare, exotic event that might account for one or two unusual galaxies, but something happening routinely across a large fraction of the early massive galaxy population. If close to half of all massive early galaxies are colliding or interacting with a neighbor, and if those interactions reliably trigger the kind of concentrated starburst capable of producing a CRISTAL-02 style wind, then finding an unexpectedly large number of massive, Already dead galaxies scattered throughout the first 2 billion years of cosmic history stops looking like a series of unrelated coincidences. It starts looking like the predictable outcome of a single underlying mechanism playing out across a universe that happened to be far more chaotic, far more collision-prone. In its youth than it is today, common enough potentially to account for a substantial share of that tenfold excess on its own. There's a broader, more reflective point worth sitting with before moving on, because it reaches beyond the early universe specifically. The Milky Way today is not in a starburst phase, and nothing about CRISTAL-02's specific situation suggests our galaxy is at any near-term risk of a similar shutdown. The conditions that trigger this kind of violent merger-driven star formation were simply far more common in the crowded, rapidly assembling early universe than they are in the comparatively calm cosmos of today. But the underlying physics doesn't care what era it's operating in. Every galaxy that has ever formed massive stars has driven at least some version of a stellar wind out into its surroundings. What changes, across cosmic time, is the intensity and frequency of the conditions extreme enough to turn that ordinary process into a galaxy-quenching event. CRISTAL-02 isn't a warning about our galaxy's future so much as a demonstration, caught directly in progress, of a process every massive galaxy has experienced in some form, somewhere in its history, just rarely, if ever, at the extreme intensity on display here. Put the two galaxies in this part side by side, and a coherent picture emerges. CRISTAL-02 shows the mechanism in progress, a galaxy actively blowing away its own fuel supply, on a countdown timer measured in tens of millions of years rather than billions. XMM Vid1 2075 shows what waits at the far end of that countdown. Quiet, massive, its stellar motion scrambled by, most likely, a single violent collision, its star formation already extinguished by the time Webb caught sight of it. Different galaxies, different specific stories, but pointing toward the same broader conclusion already building across every chapter in this video. The early universe wasn't a slow, gentle rehearsal for the cosmos we live in today. It was a faster, rougher, more violent draft, one where galaxies could grow up and burn out on a timescale that current models are still catching up to. Every thread introduced so far in this video, the little red dots, the blue and red monsters, the overmassive black holes, the speculative dark stars, and now the galaxies that finished before they should have had time to start, has been a separate piece of evidence pointing toward the same underlying conclusion gathered by different teams using different instruments studying different objects, without any of them setting out to prove a unified story. The remaining question is what all of these independent pieces add up to together once they're placed side by side. Does an early universe running faster and rougher than expected genuinely threaten the standard model of cosmology that has survived every previous test thrown at it? Or does it simply mean that model needs a more detailed, more textured picture of extreme, early conditions than it currently has? That's where this video turns next. Before going any further, it's worth taking a moment to look back at everything this video has actually covered, because taken one chapter at a time, it's easy to lose the thread connecting all of it. This isn't even the first time astronomers have had to revise how quickly the universe was capable of building itself. When Edwin Hubble first demonstrated that the universe was expanding, in the late 1920s, it forced a wholesale rethinking of cosmic timescales that had been assumed static for centuries. Decades later, the discovery of quasars, extraordinarily luminous, extraordinarily distant objects, later understood to be powered by feeding supermassive black holes, showed that extreme, energetic structures had already formed surprisingly early in cosmic history, long before Webb existed to look even further back. More recently still, the discovery of gravitational waves opened up an entirely different channel for studying violent cosmic events, including black hole mergers, that optical and infrared telescopes alone could never have fully characterized. Each of those earlier revisions felt, at the time, like a genuine crisis for the prevailing picture of the universe. Each one turned out, eventually, to be an expansion of that picture rather than its collapse. There's no guarantee this current chapter follows the same pattern. But it's the pattern every previous chapter like it has followed so far. It started with a shock. In July 2022, Webb's first deep field images turned up galaxies that looked, by every early estimate, far too bright and far too massive for how soon after the Big Bang they appeared. For a brief period, some of the loudest voices in the room suggested the entire standard model of cosmology might be in trouble. Follow-up work, patient and unglamorous, walked most of that panic back. A population called blue monsters turned out to be genuinely puzzling, extremely luminous, compact, almost entirely free of dust, but explainable through ordinary physics operating in unfamiliar, metal-poor conditions, not through any breakdown of cosmology itself. A separate population, the little red dots, turned out in most cases to be black holes in disguise, their light dominated by gas falling into a central black hole rather than by an implausibly large number of ordinary stars. Removing them from the count resolved most, though not all, of the original too massive problem. What was left over pointed toward something more interesting than a crisis, a pattern. An overmassive black hole, UHZ-1, arrived on the scene weighing about as much as its entire host galaxy, matching a theoretical prediction for heavy seed black hole formation made years before Webb ever launched. A second black hole, GN101830, showed that even a young, overmassive black hole can spend most of its life quietly dormant, punctuated by short, violent growth spurts, solving part of the timing problem without requiring anything exotic. Red monsters, dust-choked and massive, emerged as almost a mirror image of the blue monsters, and a still unconfirmed hypothesis proposed that the two populations might simply be the same galaxies, caught at different moments in the same process. And running quietly underneath all of it was one genuinely speculative idea: dark stars, hypothetical objects powered by dark matter rather than nuclear fusion, offered not as an accepted answer, but as a real, testable possibility still waiting on more data. It's worth noticing how neatly, if speculatively, that last thread connects back to the black hole seeding puzzle. If dark stars are real, and if they really do collapse into black holes once their dark matter fuel runs low, they'd hand the early universe exactly the kind of heavy, preformed black hole seed that UHZ-1's existence seems to demand, arrived at from a completely different research direction, starting from the nature of the first stars, rather than from X-ray observations of a single distant quasar. Nobody has confirmed that connection. It remains one hypothesis resting on another speculative floor built on speculative floor. But it's exactly the kind of quiet, cross-disciplinary thread that makes this particular moment in astronomy worth paying close attention to. Separate teams, working on what looked like separate problems, occasionally finding that their answers fit together. Then came the apogee, XMM-Vid-1 2075, a galaxy that had not just grown fast but finished completely. Its star formation shut off its rotation, erased less than 2 billion years after the Big Bang. Likely the result of a single violent collision rather than the billions of years of gradual merging that normally produce that structure. It belonged to a broader, independently documented pattern astronomers call cosmic downsizing, and to a specific statistical excess, massive quiescent galaxies showing up roughly 10 times more often in Webb's data than pre-Webb models predicted, that had already been flagged years before this particular galaxy's rotation was ever measured. And CRISTAL-02 showed the mechanism behind that kind of early death directly mid-process, a starburst violent enough to blow away its own fuel supply through supernova-driven winds alone on a timescale of tens of millions of years. In a universe where nearly half of all massive galaxies were colliding with a neighbor at any given moment, laid out together like that, a clear shape emerges. Almost none of these individual puzzles required abandoning the framework astronomers have relied on for decades, the mix of dark matter. Dark energy and ordinary physics, known as lambda CDM, the same model that has correctly predicted the cosmic microwave, background the large-scale structure of the universe and the abundance of light elements produced in the Big Bang itself. What every one of these puzzles required, instead, was a more detailed, more textured understanding of exactly how galaxies, black holes, and stars behaved under conditions the standard model had never been tested against before. Gas almost entirely free of heavy elements, galaxy densities far higher than today. A universe still young enough that even a single dramatic event could do the work that normally takes billions of years. It's worth pausing on how that process actually played out, because it's easy to remember only the dramatic headline from 2022 and skip past the years of unglamorous work that followed it. The little red dot reclassification, in particular, is worth holding up as a model of how this is supposed to go. Astronomers didn't quietly discard the inconvenient data, and they didn't stubbornly cling to the original, broken cosmology headline out of attachment to a dramatic story. They built better tools, deeper spectra instead of color estimates, larger comparison samples, more careful statistical methods, and let those tools tell them what was actually going on, even when the answer turned out to be less sensational than the initial alarm. That's not a story about science failing to predict something. It's a story about science doing exactly what it's supposed to do when it encounters something it didn't predict, getting curious instead of defensive, and following the data somewhere more interesting than the first headline suggested. The same pattern repeats in miniature across nearly every chapter of this video. A striking early number gets reported, sometimes amplified past what the underlying data actually supports. Independent teams spend months or years testing it against better instruments, larger samples, and competing explanations, most of the time. The extreme version of the claim softens into something more modest, but still genuinely surprising. Not cosmology is broken, but star formation ran hotter than we assumed, or black holes can start out heavier than we assumed. Or a single collision can do more damage than we assumed. None of those softened conclusions made the underlying story less interesting. If anything, each one replaced a vague, headline-friendly panic with something far more useful, a specific, testable mechanism with its own predictions that future observations can be checked against directly. That said, it would be dishonest to present this as a fully closed case, because the scientific community itself hasn't closed it. Some of the earliest, most extreme mass estimates from 2022 and 2023, before spectroscopic follow-up trimmed the sample down, implied that certain candidate galaxies would have needed to convert more than 80% of their available raw gas directly into stars, a number worth pausing on because prior modeling of galaxy formation had treated anything above roughly 57% efficiency as implausibly high, bumping up against a physical ceiling on how fast star formation can proceed at all. That specific tension flagged prominently at physics conferences as recently as 2025 hasn't fully vanished even after the most extreme individual candidates were reclassified or refined. It's part of why some of the star formation efficiency questions raised earlier in this video, particularly around red monsters, and the residual excess of massive galaxies remain genuinely open rather than fully resolved. The picture presented across this video, extreme but explainable astrophysics, no fundamental crisis, represents the position held by most working researchers actively studying this data, including the teams behind several of the specific resolutions covered earlier, like the little red dot reclassification. But it isn't unanimous. A smaller number of researchers have argued in peer-reviewed papers that the tension between JWST's earliest observations and Lambda CDM's predicted timeline is more serious than the mainstream position suggests, serious enough to warrant exploring genuine alternatives to the standard cosmological model. Rather than incremental fixes to galaxy formation physics within it, some of these proposals modify how light or time itself is understood to behave over cosmic distances. Others revisit long-standing separate tensions in cosmology, like the ongoing disagreement over precisely how fast the universe is expanding today, a distinct, decades-old puzzle in its own right worth acknowledging without conflating it with everything covered in this video, and ask whether an early, more efficient phase of cosmic expansion might resolve multiple puzzles simultaneously. As of a major cosmology conference held in 2025 that brought together more than 130 researchers, specifically to assess the state of these open tensions, no single alternative has gathered anything close to consensus support. And none has yet matched the standard model's overall track record across the full range of cosmological observations it explains. The fair summary, sitting at the intersection of that majority position and that persistent minority dissent, is this: nothing covered in this video has definitively broken cosmology. But the specific, patient, case-by-case work required to arrive at that conclusion, reclassifying little red dots, measuring UHZ1's black hole mass, catching CRISTAL-02's wind in the act, was not optional. It was the actual mechanism by which this looks broken became this is stranger and faster than we assumed, but still consistent. That process is ongoing, will likely remain ongoing for years, and the correct attitude toward it, watching from the outside, isn't confidence in either direction. It's patience and continued attention to what the next round of data shows. It's worth being specific, too, about what would actually shift that balance of opinion, rather than leaving the disagreement as a vague, permanent stalemate. If future, larger surveys continue to find that removing black hole-dominated objects and adjusting for realistic star formation efficiency accounts for essentially all of the remaining excess of massive early galaxies, the mainstream, no crisis position gets steadily more solid, if instead a genuine, well-measured population of galaxies keeps surfacing that can't be explained by any combination of those effects. Galaxies too massive too quickly even after every reasonable astrophysical adjustment has been applied. That's exactly the kind of result that would move a currently minority position into serious mainstream consideration. Science doesn't resolve open questions like this through authority or vote counting. It resolves them by making a proposal specific enough that reality can eventually rule it out, and then going and checking. There's a detail worth sitting with once the individual mysteries have been laid to rest, or at least mapped out. Nearly every strange object in this video shares a specific kind of strangeness, something arrived at a stage of life it hadn't earned yet. A black hole too massive for its youth, a galaxy too dusty, too settled, too still for how little time it had actually existed. We spent this entire video using the language of human development to describe them, too mature, too grown-up, aged beyond their years, because that language was the only honest way to describe what the data showed. And it's worth asking briefly what that choice of language reveals and what it might be quietly hiding. Calling XMM Vid1 2075 a galaxy that died too young is accurate, in the sense that its star formation genuinely, measurably stopped. But it's also a framing borrowed entirely from a human timescale, a human relationship to growth and decline, mapped onto a process that has no interior experience of its own at all. A galaxy doesn't know it's finished. It doesn't experience the compressed violence of a head-on collision as tragedy, the way we might narrate it. The universe's first 2 billion years weren't rushed or unfair or cut short. By any standard except the one we bring to the description after the fact, a standard built entirely from watching our own lives and the life cycles of the stars and galaxies nearest to us unfold on a particular familiar timescale. That's not a criticism of the storytelling. It's arguably the only way this material can be made comprehensible at all. Every video on this channel, this one included, works by finding the human scale hook inside genuinely inhuman timescales and processes. But it's worth remembering, once in a while, that the universe was never actually keeping a schedule it could fall behind on. There was no expected pace of maturity that the early universe failed to meet, and no cosmic clock it beat by cheating. There was only physics, gravity, gas, radiation, and dark matter, running forward under whatever specific conditions happened to exist at the time, producing whatever specific outcomes those conditions allowed. Too fast and too early are our words, describing our surprise, measured against a mental model built from a universe 14 billion years further along than the one Webb is looking at. The universe itself was simply doing, at every single moment covered in this video, exactly what its own local physics required. There's something almost freeing in that reframing once it settles in. Every strange object covered here, the overmassive black hole, the dust-choked giant, the galaxy that stopped spinning before its second birthday, stopped being an anomaly the instant its actual mechanism was understood. UHZ1 isn't cheating the rules of black hole growth. It's demonstrating a rule about direct collapse that had been theoretically predicted years before anyone found an example of it. XMM Vid1 2075 isn't defying the physics of galactic mergers. It's showing what a single, sufficiently violent version of that ordinary process can accomplish in a fraction of the usual time. Nothing in this video broke a law of physics. Every single object in it followed the rules perfectly. What broke repeatedly was a set of quiet, reasonable-sounding assumptions about how much time certain outcomes require, assumptions built by extrapolating backward from a 14 billion-year-old universe and applied to a period of cosmic history that, it turns out, simply didn't play by the same pacing. This isn't a uniquely astronomical mistake, either. Other sciences have made and corrected the same kind of error before. 19th-century geologists spent decades underestimating the age of the Earth because their models of how slowly rock layers accumulate were calibrated on processes they could observe directly, at human speed, without accounting for how differently those same processes might have behaved under more extreme ancient conditions. Evolutionary biologists spent a similar stretch of time assuming that species change gradually and continuously, before evidence accumulated that evolution often proceeds in exactly the opposite rhythm, long stretches of near stillness, punctuated by comparatively sudden bursts of rapid change, concentrated into a small fraction of the total time available. In both cases, the eventual correction wasn't, the old model was worthless. The old model quietly assumed a constant, gentle pace, drawn from whatever process was easiest to observe up close, and reality turned out to be lumpier than that. The story of the early universe told across this video is the same correction, applied to galaxies instead of rock strata or fossils. It's worth returning one last time to the specific word this entire video has been built around: mature. Every object covered here got called that, in one form or another: too mature, too developed, too grown up for its age. It's a useful word and an honest one, given how directly it captures what the data actually showed. But mature is also a word borrowed from biology, from the specific, familiar experience of watching something develop through childhood, adolescence, and adulthood, each stage taking roughly the amount of time we've come to expect. Galaxies don't have childhoods in that sense. They don't have a biologically fixed developmental clock counting down whether or not conditions cooperate. What they have is raw material, gravity, radiation, and however much time and however violent an environment happens to be available to them. Under sufficiently extreme conditions, extreme density, extreme mergers, extreme feedback, that raw material can apparently produce the structural, chemical, and dynamical signatures of maturity in a small fraction of the time such maturity usually requires, not by cheating a biological clock that was never actually running. By demonstrating that the clock we assumed was universal was really just describing one particular, comparatively gentle set of conditions, the conditions of a settled, spread-out, 14-billion-year-old universe, and not a fundamental law of how quickly complexity is allowed to emerge anywhere in the cosmos. That's the real subject of this video, underneath all the specific galaxies and black holes, not a broken universe, but an underestimated one, a cosmic dawn that ran hotter, denser, and more violently compressed than the calm, settled universe we happen to live in today ever suggested it should have. We built our expectations for how galaxies grow up entirely out of watching galaxies that had already grown up. Webb handed us, for the first time, a direct look at the part of the story that came before any of that settling happened, and the honest response to what it found isn't alarm, it's recalibration. The universe's first chapter was simply written faster and rougher than its later ones. We're only now getting to read it. There's one more angle worth considering before this video closes, and it has less to do with the galaxies themselves than with the timing of when we happen to start asking these particular questions. For the entire history of astronomy up until very recently, the specific era covered in this video, the first 2 billion years after the Big Bang, was simply out of reach. The light was too faint, too red, too deeply buried in infrared wavelengths for any instrument that existed to detect it in useful detail. The questions this video has spent 2 hours answering weren't unanswerable in principle. They were unanswerable in practice, for every single generation of astronomers who came before this one, for the entire span of human history in which people have been looking up and wondering how any of this began. That changed specifically in the mid-2020s because a large, cold, carefully shielded mirror finally reached a stable position 1 million miles from Earth and started collecting exactly the wavelengths this question required. There's nothing mystical in that timing. It's the direct, traceable result of decades of engineering, funding decisions, and specific technical breakthroughs, not cosmic coincidence. But it's still worth noticing, plainly, that we are the first generation in the entire history of looking at the sky for whom this specific chapter of cosmic history stopped being unreachable and started being something we could actually go and look at. XMM Vid-1 2075's non-rotating structure was confirmed in a study of exactly 3 galaxies. UHZ1 and GN1001830 are, between them, essentially the entire current sample of confirmed overmassive early black holes. Nearly every population covered in this video, blue monsters, red monsters, little red dots, was identified through deep, narrow surveys, covering tiny patches of sky in extraordinary detail. That depth is exactly what made these discoveries possible in the first place, but it also means the current picture is built from a relatively small number of examples, magnified into a general pattern. NASA's Nancy Grace Roman Space Telescope, currently scheduled to launch in the second half of 2026, is built to address exactly that limitation. Where Webb looks deep and narrow, Roman is designed to look wide and fast, with a field of view over 100 times larger than Hubble's, capable of surveying roughly 1 billion galaxies over the course of its primary mission. It won't outdo Webb on sheer depth or detail for any single object. What it will do is turn every one of this video's rare, individually remarkable discoveries into a statistical question that can actually be answered. Not, does an overmassive black hole like UHZ1 exist? But how many of them are there, and what fraction of early galaxies pass through a phase like CRISTAL02's on their way to becoming something like XMM Vid 1 2075? Those are the questions this video has had to leave open again and again for lack of a large enough sample, and they're precisely the questions a wide-field survey machine arriving within the year is built to close. Webb itself, meanwhile, isn't going anywhere soon, NASA's official estimate. Based on how precisely its launch trajectory was executed, puts its usable fuel supply at more than 20 years of continued science operations, meaning the specific instrument responsible for every discovery covered in this video is likely to still be actively collecting new data well into the next decade. Digging deeper into the same early universe catalog, one candidate galaxy at a time. Combine a telescope built for depth that isn't finished looking, with a new telescope built for breadth about to start looking, and the honest expectation for the next several years isn't that these questions get quietly forgotten. It's that this video's entire premise gets tested against dramatically more data than currently exists, which is exactly the outcome any of these hypotheses, majority or minority position alike, should actually want. Go back one final time to the very beginning of this video. One galaxy had already stopped growing, stopped spinning, stopped making stars altogether less than 2 billion years after the Big Bang. At the time, that sentence was designed to sound impossible. By now, it shouldn't sound impossible anymore. It should sound like exactly what a young, chaotic, rapidly assembling universe was always capable of producing, once enough of the right ingredients collided in the right place at the right moment. XMM Vid 1 2075 isn't a glitch in the story of the universe. It's a data point in a story that turned out to move faster than we assumed anyone was allowed to tell it. Consider, for a moment, everything that had to be true for this video to exist at all. A galaxy had to form, grow, collide, and go quiet, all within the first 2 billion years of a 14 billion year universe. The light from that collision had to travel outward for roughly 12 billion years, stretched the entire way by the expansion of space, before happening to cross paths with a small, cold, carefully engineered mirror sitting 1 million miles from a planet that didn't exist yet when that light began its journey. And on that planet, a species that also didn't exist yet would eventually build instruments precise enough to catch that faint, ancient signal, patient enough to spend years confirming what it actually meant, and curious enough to keep asking why, rather than simply marveling at the number and moving on. None of that had to happen, all of it did. Remember the clock from the beginning of this video, the entire 13 billion-year history of the universe compressed into a single day. Every galaxy in this video, the blue monsters, the little red dots, UHZ1, XMM Vid1 2075, CRISTAL02, belongs to those first few minutes after midnight. The sun doesn't ignite until 9 in the evening. Everything resembling a familiar, settled galaxy, spinning calmly and forming stars at a leisurely pace, arrives even later than that. What this video has actually been describing this whole time is the chaos of those first few minutes, a period so brief, on that compressed clock, that it's easy to forget how much of what makes the rest of the day possible was decided in it. That's the pattern this entire channel keeps returning to, one object at a time. The universe rarely breaks its own rules. It just keeps finding routes through them that nobody had gotten around to imagining yet. Every telescope we build is really just another attempt to catch it in the act, not to prove the universe wrong, but to find out exactly how inventive it's capable of being within the rules it's always followed. Somewhere in the data web is collecting right now, cataloged but not yet analyzed. There's likely another galaxy just as strange as the ones covered in this video, another overmassive black hole, another premature ending, another population nobody has named yet. That's not speculation for dramatic effect. It's simply how this process has worked, consistently, since the very first deep field image came back in July 2022. Every answer this video provided came from a question somebody had to notice first, buried in data that had already been sitting there, waiting to be looked at closely enough. The gap between the data exists and somebody understood what it meant has in nearly every chapter of this video turned out to be measured in months or years, not moments, a reminder that discovery and practice looks far less like a single flash of insight than like a long, patient argument with a stubborn, uncooperative universe that eventually grudgingly gives something up. If this exploration of the early universe's fastest, strangest chapter was worth your time, there's more of this kind of story waiting. The next video on this channel goes looking for another place where the timeline doesn't quite add up, where the numbers on paper and the universe's actual behavior have drifted apart, and something is waiting to be found in that gap. Subscribe if you'd like to be there when it does.